Free fall for us is going to be a special case of constant acceleration where we model the motion of an object and we assume that there is no air resistance. So typically, if we're thinking about free fall, we're thinking about an object that's going to be moving through the air. In reality, that object is going to be under the influence of the gravitational force and also air resistance. So we haven't talked about forces yet, but the gravitational force, you just need to recognize the tendency of that gravitational force is to cause all objects to move down. And so we're going to have an acceleration that is directed downward. We also, in reality, of course, objects have air resistance, right? And so air resistance is going to be due to the effect of all of the particles in the air affecting our motion. So 95-ish or more percent of this class, we are going to neglect the effects of air resistance. So anytime we're thinking about an object just kind of moving through the air, we are going to model that object as if it is moving in free fall. And so again, free fall is going to just give us a situation where we can model that motion as constant acceleration motion. Right now, we're going to model it as constant acceleration straight line motion. So we're just going to be thinking about objects moving just up and down. In chapter 4, I think we're going to talk about projectile motion. And projectile motion is still going to be free fall motion, but we're going to have objects that are moving in two directions. So we're going to go beyond our straight line motion. So anytime we're thinking about idealized motion of our objects under the influence of gravity only, we're going to think free fall. Of course, this, again, only happens in reality in a vacuum. And there's a really, really good video I'll link in the in Canvas that Brian Cox did, where they did the classic feather in a bowling ball experiment, and they did it in a really giant evacuated chamber vacuum. Is a really cool video. So I recommend you watch that. So if you see that demonstrates a couple of these points that you want to recognize here, which if we're modeling something in free fall, and no air resistance, then two objects that are dropped at the same height. So it's going to be independent of mass, two objects dropped at the same height are going to hit the ground at the same time and with the same speed. And so this is something you can see in that video really, really well. This is an important thing just to remember. So if they're from the same height and they reach the ground at the same time and with the same speed, then that must mean they must have the same acceleration. And so that's kind of our big idea when we're working with free fall, is that we have a fixed or set acceleration, and that acceleration is the same regardless of what our object is. So that acceleration is what we refer to as free fall acceleration. So it is a vector. So a free fall is going to equal, so I'll put in free fall. So we don't usually write this notation, but we're just defining it here. So my free fall acceleration, this is a vector. So it's going to have some magnitude g. And the direction I'm going to just put in here is always directed down, right? So anytime something is dropped or something is going through the air, that gravitational force is pulling it down. So it's going to have that acceleration that is directed downward. So when we define this acceleration, there's the two pieces. There's g, and g has a magnitude. This is 9.8 is what we'll use in our calculations. That 9.8 is just the magnitude of the vector. So it's important to remember that acceleration is a vector. So when we're working with that acceleration, we're not ever going to say that g itself is negative. So g is just a magnitude. G itself can't be negative, but our acceleration can be negative. So the acceleration is going to have that direction piece. And depending on where we set our positive direction, that acceleration might be negative, or our acceleration might be equal to negative g. Okay, but g itself is just a magnitude. 9.8 meters per second is what we will use in this course as the value for g. And then we do always need to, as we've done so far with constant acceleration, identify our positive direction. And that will be used to help us define our acceleration, our direction of our acceleration. Okay, so let's take a quick look. So right now, we are just working with straight line motion, so objects are either going to be going up or coming down if we're dealing with free fall. So I'm going to outline just a quick little picture showing what this looks like in terms, we'll do a motion diagram and then do some motion graphs. So we'll just say this is the ground. I'll say this is y equal to 0. and we'll say that our positive direction is up. So if I throw an object upward, it's going to start with some velocity. So I'm going to have a velocity vector with some length to it. And then as soon as it leaves my hand, it's going to, imagine if you throw something upward, it's going to slow. When it gets to the top or its maximum height, it's going to stop. So if I throw something up that is in free fall, it is going to have a motion that looks, right, something like this. So this would be my start down here, and this would be my end. It is going to be constant acceleration. So that's what we're doing when we're modeling this in free fall motion. So I'm going to just do this so I have a little bit more room here. I'm going to say y is equal to 0. So I'm going to say this is position 1 and this is position 2. So since it's constant acceleration, we know, right, that we have our 6 variables, and I can put my 6 variables here. Vy2, we're going to have some acceleration through the middle or across our interval and some time. So we still have our 6 variables, just instead of x's, now these are y's. We still have the starting and ending position, starting and ending velocity, acceleration, and time across those. If I look again at the motion diagram, so my vectors are getting smaller as I go up because I'm slowing down. And that means I have an acceleration, right, that is directed down. That's going to be our free fall acceleration, or acceleration due to the gravitational force. So that is directed down. It needs to be opposite direction of my velocity vectors because we are slowing down to the top. When we're dealing with free fall, so one of the nice things about recognizing, yes, this is free fall motion, is that we always know what our acceleration is, right? So our acceleration is always going to be g magnitude, and then I need to indicate my direction. So in here, I know that the magnitude is g. I need to always check my direction. So if I say that y is positive up, my acceleration is directed down. I need to make sure and indicate that in this case, the way I have my coordinate system set up, this would be a negative g for my acceleration. When we're working with constant acceleration or working with this free fall motion, another value that sometimes we know, depending on the situation that is given, is if my y is a max, right? If this is my max height here, then I'm always going to know that this velocity, so that velocity at the top of our motion in free fall motion is going to be 0. So sometimes we'll work with a case where that's true. Sometimes we might have an interval where we want to know some height or position that's not yet at the top. And so we don't want to always automatically say that the Vy at the top of a interval is 0, but depending on your situation, that might be the case. And that might be something that we also can know just by setting up our problem. All right, this is our motion diagram. If we real quick just make a couple of motion graphs. So I'm going to do position time graph here for this. So position time graph, T is always our horizontal axis. I'm going to put y here now on the vertical axis. So we had been using x of t graphs. This is a y of t just because our position is along the y axis. So if I look at this is my 0 of my position. And so if we think about our position here, we're going to start at the 0. So down here, this is my 0. So here's my 0 position. We're moving away from that in the positive direction. So I am starting out with a big position change, right? If we think about what we did when we constructed these, when we first introduced these, my first time interval has a big position change, then a smaller and a smaller. So we're slowing down. So that means our position time graph is going to look like this, right? This is an indication that we're slowing down as time progresses. If we do our velocity time, so again, time on this axis, now we're going to have v sub y. So if I look at this one, we're starting with a big velocity and we're going to be 0 at the top. So if I look at this one, we're going to have something that looks like this. So v is equal to 0 at the bottom. I'm starting with some positive velocity. And then I can also do a acceleration time graph. So here's my acceleration in the y direction. I can look at that velocity time graph. I have a negative slope, which means I have a negative acceleration. It's a constant slope, so I have a constant acceleration. So that's going to be down here. And this, in fact, is going to be negative g, right? We know the magnitude of that acceleration is g, and it should be negative. The negative just is in reference to the coordinate system that we set up here.